forgot to introduce the man stage right, but this is Woody Woods, president of Chapter 70 of the IAC, and he will introduce our guest of honor.
Thanks, Jeff. Well, we're gratified to have all of you out here. It's no surprise, frankly. Well, for those of you who haven't, they're on sale here. So probably these people know as much about your life almost, it seems like, as you do after reading that book, Chuck. So you're among friends here, obviously. Do this for the International Aerobatics Club. The requests are just, you know, flow like Niagara Falls for him, and so this is precious time for us. We're deeply grateful for his being willing to talk with us today. And without further ado, and without taking his time, General Chuck Yeager.
I've never participated in a forum before, so I really don't know what the hell is going on. But since the International Aerobatic team at you know, who have perfected aerobatics to where they're very precise, are doing things with airplanes that we wish we could have done in World War II. And since our job back in 43 and 44, when we were flying as fighter pilots against the Germans, aerobatics are something, or acrobatics, were something that was started many, many years ago. Obviously, they were developed in World War I and some prior to World War I. And all of the terminology that you hear these guys talking about, like Luftberries and Immelmans and loops and things like that, were normally named after the people that invented that maneuver. And you have to remember, when airplanes first started flying, they flew around straight and level. And that was, it took all your efforts to keep them straight and level. And consequently, the acrobatics that we learned in 43 when we were training as fighter pilots were primarily air combat tactics. And the one thing we found out very quick, unless you could do something that a guy on your tail couldn't do, man, you're going to get shot down real quick. That makes a fast learner out of you. And consequently, the dogfighting we did in Mustangs against the Germans basically are what were the forerunners to what you see these guys doing precision acrobatics are today. And it's something that gets into your blood. And most of you watched Bob Hoover do things. You know, all he does today in an airplane is exactly what he was doing back in 43 and 44 dogfighting, except he doesn't have anybody shooting at him. So he does them a little slower. And consequently, when we first checked out in airplanes, and a lot of you people here fly, of course, in fact, almost all of you, the first thing they taught you after you learned how to take off and land in an airplane and learn formation and weather or night flying was aerobatics. And the first thing they taught you was a loop, and then they taught you rolls, and then they taught you Immelmans, and then they taught you to split S. And the one thing that you learned after practicing these maneuvers for many, many hours was that was leading you into the feel of your airplane. And the first time that I tangled with a 109 who was good enough to really get into a dogfight, I found that I had to use all of the tricks of the trade that I had been, or that I'd learned in P-39s and P-51s to keep the guy off my tail. And then once the old tide turns, you start working around on the tail of the 109 or 190, then the guy starts testing everything that you know. And basically, it's just a matter of survival. And consequently, all through my career, since being trained as a test pilot in 1946, a test pilot's job is to evaluate an airplane. And you not only evaluate it, you work up the pilot's handbooks. And you also learn about the stability and control, and sit down and write so that another pilot understands how to fly your airplane just from reading the book. And consequently, we were taught many, many different modes of test work. And you see these guys out here in pits doing hammerhead stalls or or spins and snap rolls. Spins are something that we military guys have lived with all of our life, because usually high wing loading airplanes, such as the fighters that we flew then and fly today, with the exception of the flyable wire system airplanes, usually end up in spins inadvertently, because when a guy's dogfighting, you don't pay an awful lot of attention to the ragged edge of your airplane. If some guy's making a pass at you and you want to get out of his way, you usually will honk it in so hard that the airplane will snap and you end up in a spin. And that's the first thing you learn, is spin recovery. And obviously, many airplanes, or in fact all airplanes, spin differently. And that's the first thing we learned in test pilot school, in the different spin modes that every airplane has. And consequently, you have to be a very, very knowledgeable pilot to recover from all of the spins that you can get into in a high-performance airplane. That's one of the things that we were taught early in life, was spin recovery techniques. Consequently, a lot of people have a lot of different opinions about whether to teach you as a pilot spin recovery techniques, or teach you what the approach to a stall is and let you take corrective action there. I'm for one of those that I like to learn what causes an airplane to stall and never go beyond a stall, because you can get in some pretty hairy situations with a lot of high wing loading airplanes. Now, I mentioned something a while ago. Go back a little bit. Once we were able to get airplanes, you know, like the X-1 up to Mach 1, and learned that we needed flying tails on the airplane, and then we learned how to make the wings thinner and sweep them, and then get jet engines with afterburners on them, which gave us enough thrust to drive the airplane out beyond Mach 1 or out to Mach 2. Then we ran into a little bit of a problem. And most all fighters, like especially those that we used in World War II, in order to be maneuverable, like the P-51 was, we had to make those airplanes unstable. Because the more stable an airplane is, the less maneuverable it is. And you'll see that in these aerobatic airplanes that the guys have built out here. They're very, very unstable in order to do aerobatic. And consequently, once we were able to get these airplanes up to supersonic speeds, we got bit a little bit, or got caught, because the airplane had been designed to be unstable at subsonic speeds so that it was maneuverable. And then once it passed into the supersonic regime and had supersonic flow of the whole airplane, it became stable because of this supersonic flow of the whole aircraft. And when it became stable at supersonic speed, it no longer was maneuverable. So we had to back off in airplanes like the 104 and the Century Series fighters, and make those airplanes extremely unstable at subsonic speeds so that they would be maneuverable at supersonic speeds. And this brought about stability augmentation systems that we put on all of our Century Series fighters, meaning yaw dampeners, pitch dampeners, and roll dampeners, so that they flew acceptably well at slow speeds where you did most of your air-to-ground work or dogfighting. And then when the airplane went supersonic, it became stable and you didn't need these stability augmentation systems. Now, this led to airplanes, for instance, probably the worst airplane as far as stability was concerned was the F-4 Phantom II. And we got caught, like in the Vietnam War with the F-4 Phantom II and the 105s, with airplanes that were so unstable at slow speeds in order to be maneuverable at supersonic speeds that if you departed that airplane, meaning you exceeded its maximum angle of attack limits, and the airplane snapped, the airplane was so unstable that you couldn't get it out of the spin. And so you punched out of it, and this is not a very profitable way to fly airplanes. Consequently, that's about where we were in the late 60s, early 70s. Now, something happened in the early 70s that gave us a new capability, and that was the availability of computer technology. And by the early 70s, we were taking a hard look at computers to fly our airplanes. We had a few test airplanes that were rigged up with flyable wire flight control systems or computer-actuated flight control systems, which led to the F-16, which was the first production flyable wire system. Now, what happened with computer technology becoming available, we were able to put a computer in the airplane and through a servo mechanism, let that computer fly the airplane. And all that the pilot does is make an impulse into the computer, meaning through a wire. And that's where the terminology flyable wire systems comes from. And all that he does is ask the computer that give him, say, a 3G turn, and the computer analyzes the airspeed of the airplane, and then through the servo mechanism gives him the tail angle of attack required to give him what he asked for. Now we had a lot of advantages with this new system, and you see it quite common on airplanes like the F-18 that you see flying out here, or if you fool around with F-16s and F-20s, are the three primary flyable wire system airplanes. Now, what happened then when we put that computer in the airplane? We were able to program the computer to never let the airplane exceed the angle of attack where it would depart or snap. So we were able to design an airplane, in the case of the F-16, with an aft CG, relatively large tail, and then program the computer to never let the airplane exceed its maximum angle of attack where it would snap, regardless of what the pilot calls for. And consequently, that's what we had by the mid-1975, 76 time period. Now, we only had analog computers that were available to fly the F-16. Now, we had a little bit of incompatibility between the flight control system computer, which was analog, and the weapons management systems computer, which was digital. This problem was solved when we came out with the F-18 that you see flying here. Went to straight digital systems, and consequently, one thing that was a fallout from these computer flight control systems was the tremendous amount of capacity in the computers where we could program or put information about all of the weapon systems that the pilot uses in these new airplanes. And he doesn't have to have a checklist or run around with a head full of data. It's all there in the computer. Now, consequently, this led airplanes, especially in the F-18's case, with an instrument panel that's sitting there with merely 3 cathode ray tubes in the instrument panel. And consequently, around each of these cathode ray tubes, primarily the two weapons management CRTs, is you have some 20 to 22 buttons around each of these CRTs. And each one of these buttons will bring up a weapons management system that the pilot uses, like an AIM-7 Sparrow radar beam riding missile, or an AIM-9L infrared missile, or Harpoon anti-ship missiles. All of these weapons that you can carry on an airplane like that, each one of these buttons will give you a weapon systems presentation that the pilot uses, like maximum and minimum range on his missiles, the data on his target, and once you get it up on the CRT, then you transfer it to the heads-up display, and then the pilot never goes back into the cockpit. And we further refined these weapons management system in airplanes like the F-20 today, where a pilot never takes his hand off the throttle of the stick, because in the case of the F-20, like if your CRT is sitting there and you've got 22 buttons around it, and if you want to bring up a weapon system, you know what each button handles. You run a cursor up with a button on the throttle to the weapon system you want to use, activate it, and once you get it on the CRT, then you transfer it to the heads-up display or on the windshield, and the pilot never goes back into the cockpit. And you can change frequencies, latitude, longitude input into your inertial navigation systems, or declutter your heads-up display, like take out data that you don't need in managing a certain weapon system. That's the way you fly an airplane like the F-18 and F-20 today. It's not necessary to reach up, turn on switches, or do anything. In fact, you've got your computer for value inputs into your computer itself. You've got a computer control board right in the middle of the 2 CRTs. If you want to punch in values such as latitude and longitude for your inertial navigation system, or squawks on your IFF, or radio frequency changes and the like, and consequently, it makes for a very, very effective system. Now, there's another thing that's coming about. When we buy a new airplane, like the 18 or the 20, we buy it for a 25-year life cycle. And on the average, they'll average about 25 hours per month for 25 years. And with computer technology built into the airplane today, say 10 or 15 years down the road, when a new weapon comes out, all you do is make software changes in your weapons management system in the airplane, and you can handle a new weapon without making any hardware changes or any modification to your airplane. So cost effective, it's doing very, very good. And so some of the new systems that's becoming available, like computer or laser technology today, all fighters like even starting with the 104s back some 33 years ago, fighters used inertial navigation systems. And all of these inertial navigation systems depended upon gyros for direction and very sensitive accelerometers for velocity. And that's all tied in with a little air data computer that navigates for you. And consequently, the gyros in all fighters, even up to as late as the F-18 that you see sitting out here on the ramp, used gyros to spin up. Now, these inertial navigation systems took as long as a minimum of 4 minutes or a maximum of 15 minutes to fully align themselves to get the gyros spun up to max RPM, and also the little computers to orient themselves on the surface of the Earth. Now, here about 3 years ago, laser technology made it possible to take 4 mirrors and a laser beam reflecting off these 4 mirrors, and that becomes a laser gyro spinning at the speed of light, and it's instantaneous. And consequently, you put these mirror systems on 3 axes, and that's the new ring laser inertial navigation systems that became available to us to put in the F-20. And consequently, when you get in the F-20, turn the battery switch on, hit the INS align button before you do the starter, and before the engine gets up to idle, which takes 25 seconds, your INS ready light's blinking, and it's fully aligned. So that gives us a reaction capability. That's some of the new technology that's coming about. Now, a lot of you people say, what about systems like these being difficult to maintain or work on? Like if you fly these fly-by-wire systems like the F-16, 18, or 20, and when I talk about a computer, I'm not talking about one little single desktop type computer. We're talking about 18 to 20 computers all tied together with multiplex buses in the 18 F-20, where they constantly are talking to each other and aligning themselves, so you have no failures. Everything is hip deep in redundancy, and they're very, very good systems. And consequently, what happens after a flight, when you taxi back in, these computers monitor trend failures in either hydraulic systems, electrical systems, or fuel systems, or all of the systems that you carry on your airplane. And consequently, when you park the airplane, your ground crew comes up, plugs into the computer, and says, "Hey, what systems are bad on my airplane?" And the computer will tell him not only what systems are going bad or are bad, but what black boxes to fix them, to change to fix them. And so it makes for a very, very easy airplane to maintain. That's what we're after. And airplanes that you see flying today, like F-15s, F-16s, and especially F-14s out here, the maintenance man-hours required to support one flying hour on airplanes like the F-14, F-15 are astronomical. They're running anywhere from 35 to 40 hours versus one flying hour. And what you've done with this new technology that's going into airplanes like the F-18, we're reducing that down now to where the F-18 takes an average of about 7 to 8 maintenance man-hours for one flying hour. And in the case of the F-20, we've got that down to 5. And that's what we're after, because that's where your money goes down the drain in buying maintenance and the cost to operate these airplanes. And when you're flying a few hundred of them, a lot each month, that's a pretty fabulous amount of money going down the drain for maintenance costs. And that's what we're after. Airplanes that have systems that have mean time between failures that run into the thousands of hours. And systems like the ring laser INS, which has no moving parts, are the kind of technology that we're putting into these airplanes. And consequently, some of these new systems, you see aviation, over the period of time that I've been fooling around with it since 42, you see it take a quantum jump and level off, a jump and level off. And today, with new technology becoming available, not only in the advanced tactical fighters, but advanced tactical bombers, and also the ability to apply stealth technology, these new airplanes, we're really taking a big jump now, especially with the new systems that are available to us to put in these airplanes. It's fun to stay abreast on the development of airplanes like that. I do a lot of work on the F-20, and I get in a 15 or 16 or F-4 or an 18 once in a while just to stay abreast of the new technology. Now, I know if you have any questions, I'll be happy to answer.